The vast enigmatic expanse of space has always fascinated humanity. Yet, beyond its breathtaking beauty lies a terrifying and often overlooked truth. The universe is a chaotic, violent, and unrelenting force filled with cosmic horrors beyond imagination. Picture the unimaginable power of a black hole, an entity so dense that not even light can escape its gravitational grip, warping time and space itself, stretching matter into oblivion, swallowing entire stars without a trace, and lurking unseen in the darkest corners of the cosmos, waiting to consume anything that dares to stray too close. Imagine the terrifying fate of rogue planets, massive celestial bodies wandering the endless void without a star to anchor them, drifting aimlessly through the abyss, their surfaces frozen in eternal darkness, yet potentially harboring unseen dangers or even life forms adapted to their extreme conditions. Consider the eerie silence of the Fermi paradox, a question that haunts scientists and dreamers alike. If the universe is teeming with planets and the potential for intelligent life, why have we found no evidence of extraterrestrial civilizations? No messages, no artifacts, only an unbroken silence stretching across the cosmos. What if the reason for this silence is more sinister than we dare to imagine? What if an unknown cosmic force has systematically erased civilizations before they could reach us? Or what if we are simply too insignificant for higher beings to acknowledge our existence? The possibility of gamma-ray bursts, the most powerful explosions known to science, capable of sterilizing entire galaxies with their unimaginable energy, sends chills down the spine. For if one were to occur close enough to Earth, our atmosphere could be stripped away in an instant, leaving us exposed to the deadly radiation of space, wiping out life as we know it, before we could even comprehend what was happening. Then there are the pulsars, remnants of once massive stars, their immense magnetic fields generating beams of radiation that sweep across space like celestial lighthouses, emitting signals so precise and rhythmic that early astronomers once mistook them for potential alien beacons. Yet their mere presence is a reminder of the violent stellar deaths that forged them. Consider also the vast cosmic voids, unimaginably large regions of space almost completely empty, stretching for millions of light years, where galaxies are sparse and darkness reigns supreme, areas where time seems to stand still, a haunting reminder of the universe's incomprehensible scale and the sheer insignificance of our existence within it. What if somewhere in those voids lies something beyond our comprehension, a force or entity untouched by time and space, something watching, waiting? Meanwhile, supermassive black holes at the centers of galaxies hold entire star systems in their thrall, their immense gravitational pull shaping the fate of millions of celestial bodies, some of which are doomed to spiral inwards and be torn apart, their very atoms stretched into streams of energy in an event horizon that marks the boundary between existence and absolute oblivion. Then there is the terrifying concept of vacuum decay, a theoretical yet chilling possibility suggesting that our universe exists in a false vacuum state, meaning that at any moment, a quantum fluctuation could trigger a bubble of true vacuum expanding at the speed of light, erasing everything in its path instantly, without warning, without pain, and without any hope of escape. The reality of space is not just about majestic galaxies and twinkling stars, but about the relentless forces that govern the cosmos, forces that neither know nor care about our existence. A universe that is as ruthless as it is beautiful, where celestial bodies collide in cosmic cataclysms, where stars are born only to die in violent supernovae, leaving behind remnants that either scatter their elements to create new worlds or collapse into monstrous singularities from which no information can escape. The sheer unpredictability of what lies beyond our solar system, the potential for deadly asteroids, planet-killing comets, or unknown cosmic anomalies that could disrupt the delicate balance of our planet, looms as an ever-present reminder that while we look up at the stars with wonder, we do so with blissful ignorance of the countless ways the universe itself is indifferent to our survival. From the dawn of civilization, humanity has gazed at the night sky with a mixture of wonder, fear, and curiosity, seeking to understand its vast mysteries and our place within it. Early civilizations such as the Babylonians, Egyptians, and Greeks made some of the first recorded attempts to study celestial bodies, developing rudimentary models of the cosmos based on their observations. The Babylonians, for example, meticulously recorded planetary movements, allowing them to predict celestial events such as eclipses, though they interpreted them through a mythological and astrological lens rather than a scientific one. The ancient Egyptians aligned their pyramids with celestial bodies, demonstrating an awareness of the predictable nature of the stars. The Greeks, however, were among the first to approach astronomy with a more systematic and logical framework, with philosophers such as Pythagoras and Anaximander proposing early ideas about the Earth's place in the universe. Ptolemy's geocentric model, which placed Earth at the center of the cosmos with celestial bodies orbiting in perfect circles, dominated Western thought for over a millennium, deeply influencing medieval European and Islamic scholars who sought to reconcile it with religious doctrine. The shift from a geocentric to a heliocentric model of the universe marked one of the most profound changes in human understanding, driven by the Renaissance and the scientific revolution. In the 16th century, Nicolaus Copernicus challenged the long-standing Ptolemaic system with his revolutionary heliocentric model, arguing that the Sunday, not Earth, was the center of the known universe. His work was met with resistance, but it laid the foundation for future astronomers such as Johannes Kepler, who refined Copernican theory by demonstrating that planetary orbits were elliptical rather than perfect circles, and Galileo Galilei, whose telescopic observations provided the first direct evidence that the heavens were not immutable. Galileo's discovery of Jupiter's moons, the phases of Venus, and the rugged surface of the moon shattered the Aristotelian notion of celestial perfection and lent credence to the heliocentric model. However, his findings were deemed heretical by the Catholic Church, leading to his infamous trial and house arrest, a stark reminder of the tensions between scientific discovery and prevailing religious beliefs. As the scientific method took hold, Isaac Newton's formulation of the laws of motion and universal gravitation provided a mathematical framework that explained the movement of celestial bodies with unprecedented precision. His work, outlined in Principia Mathematica in 1687, unified terrestrial and celestial mechanics under the same principles, demonstrating that the same force governing the fall of an apple also dictated the orbits of the planets. This breakthrough not only validated Kepler's laws, but also set the stage for classical mechanics, which dominated physics for over 2 centuries. With Newtonian mechanics in place, astronomers could predict planetary motions with remarkable accuracy, leading to discoveries such as the identification of Neptune based on irregularities in Uranus's orbit. The expansion of observational astronomy, fueled by increasingly sophisticated telescopes, allowed scientists to peer deeper into the cosmos, leading to the realization that the Milky Way was not the entire universe, but merely one of countless galaxies. The 20th century witnessed some of the most groundbreaking discoveries in cosmology, fundamentally altering our understanding of the universe. In 1915, Albert Einstein introduced his general theory of relativity, which redefined gravity not as a force, but as the curvature of space-time caused by mass. His equations predicted the possibility of black holes, gravitational waves, and the expansion of the universe, phenomena that would later be confirmed by observational evidence. Shortly thereafter, Edwin Hubble's observations of distant galaxies revealed that they were receding from us, leading to the formulation of Hubble's law and the realization that the universe was expanding. This discovery provided strong evidence for the Big Bang theory, which posited that the universe had originated from a singular, extremely hot and dense state roughly 13.8 billion years ago. The detection of the cosmic microwave background radiation in 1964 by Arno Penzias and Robert Wilson further cemented the Big Bang theory, as it provided a fossilized remnant of the universe's infancy, a faint echo of the radiation left over from the birth of everything we know. Parallel to these theoretical advances, the 20th and 21st centuries have been defined by rapid progress in space exploration, allowing humanity to transition from merely observing the universe to actively exploring it. The launch of Sputnik, won by the Soviet Union in 1957, marked the dawn of the space age, followed closely by the first human spaceflight by Yuri Gagarin in 1961. The United States responded with the Apollo program, culminating in the historic moon landing of Apollo 11 in 1969. When Neil Armstrong and Buzz Aldrin became the first humans to set foot on another celestial body, Since then, space exploration has expanded beyond the moon to robotic missions investigating the outer planets, landers and rovers exploring Mars, and the launch of space telescopes such as Hubble, which has provided breathtaking images and invaluable data about distant galaxies, exoplanets, and the large-scale structure of the cosmos. The establishment of the International Space Station, ongoing missions to study asteroids and comets, and ambitious plans to return humans to the moon and eventually to Mars highlight humanity's growing ability to reach beyond our home planet. One of the most fundamental concepts in modern cosmology is that of the observable universe, the region of space from which light has had time to reach us since the beginning of the cosmos. Due to the finite speed of light and the expansion of the universe, the observable universe has a horizon beyond which we cannot see. Even with the most powerful telescopes, this means that while we estimate the universe to be at least 13.8 billion years old, the actual size of the observable universe is much larger, approximately 93 billion light-years in diameter due to the ongoing expansion of space. The notion that the universe extends beyond what we can observe raises profound questions about its true scale, structure, and the potential existence of regions that may follow different physical laws or harbor civilizations far beyond our detection capabilities. The cosmic microwave background radiation serves as a boundary to our observations, marking the limit of what we can detect from the earliest moments of the universe's formation. As our technology advances, new discoveries continue to reshape our understanding of the cosmos. The study of dark matter and dark energy, which together make up roughly 95% of the universe's total mass energy content, presents one of the greatest challenges in modern physics, as neither can be directly observed with current instruments. Yet their effects on galactic motion and cosmic expansion are undeniable. The detection of gravitational waves by LIGO in 2015 confirmed another of Einstein's predictions, opening an entirely new way of studying cosmic events, from black hole mergers to neutron-star collisions. The launch of the James Webb Space Telescope promises to extend our reach even further, allowing us to peer into the early universe and study exoplanetary atmospheres in unprecedented detail. With ongoing research into the potential for extraterrestrial life, the search for biosignatures on exoplanets, and the development of interstellar exploration technologies, the future of cosmology and space exploration holds boundless possibilities, continuing the legacy of inquiry and discovery that has defined humanity's quest to understand the universe from the very beginning. The vast, infinite stretch of the cosmos is more than just a collection of stars, galaxies, and distant planets. It is a reflection of humanity's deepest fears, greatest aspirations, and most profound questions about existence. From the moment we first looked up at the night sky, we have felt an inexplicable connection to something far greater than ourselves, something so immense and unknowable that it evokes a spectrum of emotions, from wonder to terror. The universe, in its boundless complexity, serves as both a source of comfort and a reminder of our insignificance, a duality that has captivated philosophers, scientists, and dreamers for millennia. But why should people care? What does the universe, with its black holes, supernovae, and distant exoplanets, have to do with the everyday struggles, hopes, and dreams of individuals on a small blue planet orbiting an average star in the outskirts of an unremarkable galaxy? The answer lies in the profound emotional and existential impact of the cosmos, the way it challenges our understanding of reality, our sense of purpose, and the fragile nature of life itself. At the heart of our fascination with the universe is an overwhelming sense of awe, an emotion that has the power to shift our perspective and expand our understanding of our place in the grand scheme of things. The first time someone sees an image of the pillars of creation, a breathtaking structure of gas and dust where new stars are born, or a photo of Earth from deep space, appearing as nothing more than a pale blue dot, they are struck by a realization that transcends words. This is the same feeling astronauts describe when they look at Earth from orbit, a sensation known as the overview effect, where the petty divisions and concerns of human life fade in the face of the vast and interconnected reality of existence. The universe humbles us, showing us that while we are small, we are also a part of something infinitely larger. Every atom in our bodies was forged in the heart of a dying star, meaning that the very essence of who we are is cosmic in origin. We are not separate from the universe. We are an expression of it, living, breathing manifestations of the same processes that created galaxies and nebulae. To ignore the cosmos, to turn away from its wonders, is to turn away from the story of ourselves. Yet, alongside this wonder, is an undercurrent of fear and existential dread that arises when we truly grasp the incomprehensible scale of the universe and the forces at play within it. Space is not just a realm of beauty. It is also an abyss of terrifying, inescapable realities. Consider the darkness that stretches for billions of light years, the cold, empty void where entire galaxies drift apart with no hope of ever reconnecting. Imagine the silence, the absence of air, of life, of warmth, a place where even the loudest screams would be swallowed by nothingness. The thought of a black hole, an object so dense that it warps space and time itself, where anything that crosses its event horizon is doomed to an eternity of gravitational imprisonment, is a concept so unsettling that it defies human intuition. Then there is the possibility of cosmic catastrophes. Beyond our control, a gamma ray burst from a dying star, an asteroid impact, a supernova explosion close enough to strip away Earth's atmosphere. These are not mere sci-fi scenarios, but real possibilities, reminders that the universe is not built for us, that we exist in a delicate balance, one that could be disrupted at any moment. This combination of wonder and fear makes space deeply personal, touching something primal within us. It reminds us of our mortality, of the fleeting nature of human existence, yet also sparks an unquenchable thirst for discovery. This is why we send probes to the outer planets, why we build telescopes capable of peering billions of years into the past, why we dream of walking on Mars. We seek to understand because understanding is a form of survival, a way of making sense of an existence that often feels chaotic and unpredictable. In the face of cosmic indifference, we assert our presence through exploration, through knowledge, through the sheer audacity of asking, what if? What if we are not alone? What if life exists elsewhere, thriving on some distant exoplanet or in the subsurface oceans of Europa? The mere possibility forces us to rethink everything we know about biology, evolution, and consciousness itself. If we are alone, then the responsibility to protect and cherish life becomes even more urgent. If we are not, then what would it mean to meet another intelligent species, to communicate across the void, to realize that we are not the center of the cosmic story? This yearning to understand is deeply human. It is the same force that drove our ancestors to cross oceans, to climb mountains, to push beyond the limits of what was thought possible. Every discovery, every new piece of the cosmic puzzle adds another chapter to the story of who we are and where we come from. The discovery of exoplanets in the habitable zone of their stars ignites our imagination. Could one of them be home to life, to civilizations that have looked at their own night skies and wondered the same things we do? The detection of gravitational waves confirms theories proposed a century ago, proving that even in the vast emptiness of space, invisible ripples travel across the fabric of reality itself. The mapping of the cosmic microwave background reveals the faint echoes of the Big Bang, a glimpse into the birth of time and space as we know it. Each of these milestones is not just a scientific achievement, but a human one. Proof that even on our small planet, bound by gravity and time, we have the capacity to reach beyond ourselves. Perhaps the most emotionally gripping aspect of our cosmic journey is the idea that we are living in a brief but extraordinary moment in the history of the universe. We exist at a time when we have the technology to look deep into the past, to witness the light of galaxies that formed billions of years ago, yet we are also at the mercy of a future we cannot fully predict. The universe will continue to evolve long after we are gone. Stars will be born and die, galaxies will drift apart, and one day, even the last remnants of starlight will fade, leaving behind a cold, dark cosmos in which time itself seems meaningless. The knowledge that everything we love, everything we have built, and everything that makes us human is temporary can be a heavy burden. Yet, instead of despair, it should inspire urgency, and urgency to explore, to create, to leave something behind that matters, to make our brief existence count. It is why we write books, compose music, build monuments, and strive for greatness. We may be temporary, but our curiosity, our drive, and our desire to reach for the stars are eternal. At its core, The story of the universe is a story of us. It is a story of emergence, of struggle, of discovery. It is a story of staring into the abyss and daring to ask what lies beyond. Every time a child looks up at the stars and wonders about other worlds, every time an astronomer uncovers a new truth about the cosmos, every time a spacecraft sends back images from the edge of the solar system, we are continuing a journey that began long before us and will continue long after. Whether through scientific progress, philosophical inquiry, or simply the act of dreaming, our connection to the universe is unbreakable. We care because we are a part of it, because its mysteries are our mysteries, and because the simple act of looking up at the night sky reminds us that no matter how small we may feel, we are, in some way, infinite. Have you ever truly thought about what it means to exist in a universe so vast that our entire planet, our history, our collective experiences are nothing more than a microscopic fraction of reality? Consider for a moment the sheer scale of what lies beyond our everyday lives. The observable universe stretches 93 billion light-years across, yet that is only the part we can see. What exists beyond that boundary? Is it an infinite expanse of galaxies, an alternate version of our universe, or something beyond our comprehension? More importantly, does knowing this change the way you see yourself, your problems, your purpose? When you step outside on a quiet night and look at the stars, do you feel insignificant, or does it ignite a sense of wonder, a realization that you are part of something unimaginably grand? What if we are not alone? What if, orbiting some distant star, intelligent beings are asking themselves the same questions, looking up at their own night sky, wondering if someone somewhere is doing the same? If the discovery of microbial life on another world were announced tomorrow, how would it change your perception of existence? Would it make the universe feel less lonely or more mysterious? Think about the mysteries we have already uncovered. The idea that the universe began as an infinitely small singularity and exploded outward in an event we call the Big Bang is difficult to grasp. Yet it is supported by nearly a century of research. But what came before the Big Bang? Was it the beginning of time? Or was it merely one event in a cycle of cosmic rebirth? The existence of black holes, regions of space where gravity is so strong that not even light can escape, raises equally profound questions. If nothing can escape a black hole, where does all the information about the objects that fall into it go? Does it vanish forever? Or does it remain encoded on the event horizon, as some physicists theorize? And what happens if you were to fall into one? Would time slow down for you while the rest of the universe accelerated into the future? Or would you be stretched infinitely thin, torn apart at the atomic level, doomed to become one with the singularity? What do these questions mean for our understanding of reality itself? Every major discovery in space has rewritten our understanding of the cosmos, and yet we are still in the infancy of exploration. The fact that we now know of thousands of exoplanets, planets orbiting other stars, suggests that our solar system is not unique. Among these distant worlds, some reside in the habitable zone of their stars, where conditions might allow for liquid water and, perhaps, life. The James Webb Space Telescope has already begun analyzing the atmospheres of these worlds, searching for signs of oxygen, methane, or other biosignatures that might hint at life beyond Earth. If we were to find unmistakable evidence of life elsewhere, would it challenge religious beliefs, philosophical outlooks, or societal structures? Would it force humanity to unite in a way we never have before, recognizing that we are not separate nations or cultures, but a single species in the vastness of the cosmos? Or would it bring new anxieties, the fear of the unknown, the fear of what or who might be out there watching us as we watch them? The mysteries of dark matter and dark energy present some of the most perplexing challenges in modern physics. We know that galaxies rotate in a way that defies our understanding of gravity, suggesting the presence of an invisible mass dark matter that makes up about 27% of the universe. Yet, despite decades of searching, no one has directly detected it. What if dark matter is not just a missing piece of physics, but an entirely new type of reality that we have yet to comprehend? Dark energy is even stranger, driving the accelerating expansion of the universe, meaning that, over time, galaxies will drift further apart until one day, the night sky will go dark, with no visible stars beyond our own. If this acceleration continues, the ultimate fate of the universe might be a slow death, a heat death where all stars burn out and the cosmos is left in eternal darkness. What does it mean to live in a universe that has an expiration date? Does it make our time more precious, knowing that existence itself has limits? But what if there are other universes, parallel realities with different physical laws, different histories, maybe even different versions of ourselves? The theory of the multiverse suggests that our universe might be one of countless others, each slightly different from the last. If true, it would mean that every choice you have ever made, every possibility you have ever imagined, might have played out in another reality. Somewhere, another version of you might have made a different decision, taken a different path, lived a different life. Does this idea excite you or unsettle you? If we could one day interact with these parallel worlds, would we want to? Could we ever understand the consequences of such a discovery? Even within our own solar system, mysteries persist. Beneath the icy crust of Europa, Jupiter's moon, lies an ocean with more water than all of Earth's oceans combined. Scientists speculate that hydrothermal vents, similar to those found at the bottom of our own oceans, could provide the necessary conditions for life. If microbial organisms exist there, it would suggest that life is not an anomaly, but a natural consequence of the universe's processes. Would that make us feel more connected to the cosmos, or more insignificant? If we were to discover an ancient civilization on Mars, remnants of a long-extinct race that once thrived when the planet had rivers and lakes, what lessons would we learn? Would we see a reflection of our own potential future? A cautionary tale about planetary change and survival? Space exploration itself is on the brink of a new era, with humanity preparing to become an interplanetary species. NASA, SpaceX, and other space agencies are actively working on plans to return humans to the moon and establish a presence on Mars. Within our lifetime, we may witness the first human colony beyond Earth, a moment as significant as when our ancestors first left Africa to explore new lands. Would you want to be one of the first settlers on Mars? Could you leave behind everything you know for the chance to be part of something historic, something that could ensure the survival of our species? What if you were given the opportunity to travel even further, to explore the icy moons of Saturn, the methane lakes of Titan, or even the depths of interstellar space? Would the thrill of discovery outweigh the loneliness of the void? These questions are not just theoretical. They are at the heart of what it means to be human, to question, to explore, to push the boundaries of knowledge, to dream of what lies beyond. Every new discovery expands our understanding of reality and forces us to rethink our place in the cosmos. The more we learn, the more we realize how much remains unknown. Will we ever find the edge of the universe? Will we ever understand what existed before time began? Are we truly alone? Or are we simply too young, too primitive to recognize the signs of life that may already surround us? Now, I ask you, what do you think? What excites you most about the mysteries of space? What terrifies you? Do you believe we will find life beyond Earth in our lifetime? Or do you think we are alone in this vast cosmic ocean? What discoveries do you hope to see in the future? And how do they shape the way you see yourself and humanity's future? The universe is not just a distant abstraction. It is the ultimate stage upon which our existence plays out. It challenges us to think bigger, to dream further, and to never stop questioning. Join the discussion, share your thoughts, and keep looking up, because the greatest discoveries are yet to come. The cosmos stretches endlessly beyond what the human mind can fully comprehend. An abyss of unfathomable scale where galaxies collide, stars are born and die in spectacular detonations, and invisible forces shape the very fabric of reality. Imagine drifting through the void, beyond the reaches of our solar system, beyond the familiar constellations of the night sky, into the intergalactic darkness, where space is no longer dotted with stars, but a silent emptiness stretching for millions of light years. Here, in the great cosmic voids, gravity is too weak to pull matter together, and the universe itself appears nearly vacant, save for the occasional flickering of distant quasars, ancient beacons of supermassive black holes feeding on the remnants of shattered worlds. This is the great unknown, where the vastness is not just physical, but existential, where humanity's greatest questions echo without answers. Yet within this emptiness, Galaxies spin in gravitationally bound clusters, grand cities of stars stretching across unimaginable distances. The Milky Way, our home galaxy, is a spiraling vortex of dust, gas, and billions of suns. A single member of the local group, which itself is a mere speck within the greater Laniakea supercluster, a gravitationally linked collection of galaxies spanning 520 million light-years. Every speck of light in the night sky, every star, is part of a much greater structure, swirling in perfect cosmic choreography, held together by the enigmatic force of dark matter, an unseen presence that permeates the universe, binding galaxies with its ghostly influence. Unlike ordinary matter, dark matter does not interact with light, rendering it invisible. Yet its gravitational pull is undeniable, sculpting the universe on the grandest scales, bending light from distant galaxies in an effect known as gravitational lensing. Without it, galaxies as we know them could not exist. Yet, despite decades of searching, no one knows what dark matter truly is. Is it composed of undiscovered particles? Or is it something even more elusive, a fundamental aspect of space-time itself? Then there is dark energy, an even greater mystery, an unseen force driving the expansion of the universe at an ever-increasing rate. While gravity should, in theory, slow the expansion, observations from distant supernovae reveal that the opposite is happening. The universe is accelerating outward, as if propelled by an unknown force. Dark energy accounts for roughly 68% of the universe's total energy content, yet it remains one of the most perplexing enigmas in modern physics. Some theories suggest it is a property of space itself, a vacuum energy that grows as the universe expands, while others propose more exotic explanations, such as the existence of hidden dimensions or new fundamental forces. The implications are profound, for if the expansion continues unchecked, galaxies will drift ever further apart until, one day, the night sky will grow empty, the universe becoming a cold, dark void where no new stars are born, and only the remnants of once vibrant galaxies remain. Among the celestial marvels that populate this vast expanse, some stand as the universe's most awe-inspiring spectacles. The pillars of creation, towering columns of interstellar dust and gas in the Eagle Nebula, are a birthplace of stars, where gravity pulls matter together until the pressure ignites nuclear fusion, bringing new suns to life. These stellar nurseries are scattered throughout the cosmos, forming the engines that drive the evolution of galaxies. But just as stars are born, they also die, and their deaths are among the most violent and transformative events in the universe. A supernova, the explosive death of a massive star, can outshine an entire galaxy for a brief moment, scattering heavy elements into space, seeding the formation of new worlds, and leaving behind the remnants of collapsed Corsair neutron stars, whose densities are so extreme that a sugar cube-sized piece would weigh billions of tons, or black holes, the ultimate cosmic abyss, from which nothing, not even light, can escape. Black holes are among the most feared and fascinating objects in the universe, bending space and time to their will. At the center of most galaxies, including our own, lurks a supermassive black hole, millions or even billions of times the mass of our Sunday, exerting an irresistible pull on everything within its vicinity. These titanic structures can remain dormant for eons, yet when they awaken, they devour matter with unimaginable force, forming luminous accretion disks of superheated gas spiraling toward oblivion. The energy released in the process is so intense that it can launch jets of plasma at nearly the speed of light, visible across billions of light years. And yet, for all their power, black holes hold some of the deepest mysteries in physics. What happens to information that falls into one? Is it truly lost forever? Or does it persist in some form, perhaps on the event horizon itself? Could black holes be gateways to other universes, as some theorists suggest? Or do they lead to an ultimate end? A place where the known laws of physics cease to function. In the quest to understand these cosmic phenomena, key figures in the field of cosmology have shaped our knowledge, pushing the boundaries of what we know and what we dare to imagine. Albert Einstein's general theory of relativity laid the foundation for modern cosmology, describing gravity not as a force, but as the curvature of space-time itself, predicting the existence of black holes and gravitational waves long before they were observed. Edwin Hubble's discovery that the universe is expanding transformed our understanding of the cosmos, leading to the formulation of the Big Bang Theory, the idea that the universe originated from a singular point of infinite density. More recently, figures such as Stephen Hawking contributed groundbreaking insights into black hole thermodynamics, proposing that black holes are not entirely black but slowly evaporate over time due to quantum effects, a phenomenon now known as Hawking radiation. Meanwhile, Vera Rubin's pioneering work on galactic rotation curves provided the first strong evidence for the existence of dark matter, a discovery that continues to shape the field of astrophysics. Scientific curiosity drives these explorations, yet underlying it all is a sense of profound mystery, a recognition that for all we have uncovered, we are only scratching the surface of what there is to know. The more we learn, the more questions arise what lies beyond the observable universe. If we could travel far enough, would we reach the edge of existence? Or would we find an infinite expanse of galaxies stretching forever? Is our universe the only one? Or is it part of a vast multiverse, where alternate versions of reality unfold in parallel, each governed by different physical laws? And perhaps the most haunting question of all, if the universe is so vast, why have we not yet encountered signs of extraterrestrial intelligence? The Fermi paradox looms over us, suggesting that either we are truly alone in the cosmos, or that civilizations inevitably self-destruct before they can venture beyond their homeworlds. This blend of awe and uncertainty defines our relationship with the universe. It is a place of incomprehensible beauty and unimaginable terror, a realm where existence and non-existence are separated by the thinnest of margins. Every new discovery, from the detection of gravitational waves rippling through space-time to the identification of exoplanets with the potential for life, adds another piece to the puzzle, yet the full picture remains elusive. The cosmic stage is grand, and we are but fleeting players upon it. But within us lies the same matter that formed the stars, the same elements forged in the heart of supernovae billions of years ago. To explore the universe is to explore ourselves, to seek answers to questions that have driven us since the dawn of consciousness. And so, as we gaze into the night sky, let us not see only distant points of light, but the echoes of a cosmic history, billions of years in the making. Let us embrace the wonder and the mystery, knowing that we are part of something vast and unknowable, yet intimately connected to it. The universe is not just a place we inhabit, it is the very fabric of our existence, the greatest story ever told, waiting for us to turn the next page. The universe, as we perceive it, is an intricate tapestry woven from mathematics, physics, and the limits of human observation. Yet the deeper we probe into its nature, the more we realize that we may never find a true edge, a final answer that encapsulates all of existence. Every discovery that has expanded our understanding has simultaneously introduced new, often paradoxical questions, leading us to a point where we must confront an unsettling reality. Our search for the ultimate boundary of the universe may be an endless endeavor, not because we lack the will, but because reality itself may not have an edge in the way we imagine. If we are to glimpse the outermost limits of existence, we must first accept that our very methods of observation, the fundamental laws we rely upon, and the constraints of our position within space-time may forever prevent us from comprehending the full scope of what lies beyond. One of the most significant barriers to defining an edge to the universe is the nature of the observable universe itself. Because light takes time to travel, we are always looking into the past whenever we observe distant objects. The most ancient light we can detect, the cosmic microwave background radiation, originates from roughly 380,000 years after the Big Bang, forming a sort of visual boundary to our cosmic perspective. Yet, even this is not the true beginning. Before this moment, the universe was an opaque plasma where photons could not travel freely, meaning we will never be able to observe light from the first instance of existence. What then lies beyond this veil? Could there be remnants of previous universes, cosmic structures beyond our reach, or an entirely different set of physical laws governing an unseen reality? The observable universe is only a fraction of the whole, yet there is no way for us to determine how much more remains hidden beyond our horizon. Adding to this mystery is the accelerating expansion of the universe, a discovery that fundamentally altered our understanding of cosmology. Distant galaxies are receding from us at an ever-increasing rate due to the influence of dark energy, meaning that there are regions of the universe that are moving away faster than the speed of light relative to us. Because no signal can travel faster than light, these galaxies will eventually cross a threshold beyond which their light can no longer reach us, effectively erasing them from our observable reality. This means that, over time, more and more of the universe will become inaccessible, locked away by the relentless expansion of space-time. If there is an edge, we may never reach it, not because it does not exist, but because the very fabric of reality ensures that it is always receding beyond our grasp. Physics itself is riddled with paradoxes that hint at fundamental limits to human understanding. One of the most profound of these is the problem of quantum mechanics and general relativity, two pillars of modern physics that describe the universe on vastly different scales, yet remain fundamentally incompatible. General relativity governs the large-scale structure of space-time, explaining the motion of planets, galaxies, and the expansion of the cosmos. Quantum mechanics, on the other hand, describes the behavior of particles at the smallest scales, where reality itself seems to dissolve into a probabilistic haze of wave functions and uncertainty. When we try to merge these two theories, contradictions arise, particularly in extreme environments, such as the singularity at the center of a black hole, or the instant of the Big Bang. If our current understanding of physics breaks down at these extremes, how can we be certain that our concept of an edge even makes sense? What if the true nature of reality exists in a form we are not yet capable of comprehending? Even our understanding of time itself is suspect, with some physicists proposing that time is not a fundamental property of the universe, but an emergent phenomenon arising from deeper, hidden laws. If time itself is not absolute, then the very way we define the expansion, evolution, and potential boundaries of the universe may be flawed. Could it be that what we perceive as the Big Bang was not a singular event but one phase of an eternal cycle? Some theories, such as the conformal cyclic cosmology model proposed by Roger Penrose, suggest that the universe undergoes infinite cycles of expansion and contraction, each Big Bang merely the rebirth of a new cosmic age. If this is true, then searching for an ultimate boundary might be as futile as trying to find the edge of a circle. The universe may have no beginning or end, only transitions from one state to another. The multiverse hypothesis presents yet another layer of complexity, proposing that our universe may be just one of an infinite number, each with different physical laws, dimensions, or even variations of reality itself. If this is true, then the edge of our universe may simply be a transition into another universe, one that we will never be able to perceive because our physics, our particles, and even our consciousness may be limited to this particular bubble of existence. Some theories suggest that quantum fluctuations in the early universe could have given rise to pocket universes, each expanding independently, leading to a cosmic landscape where universes are constantly being created and destroyed. If such a structure exists, then our search for a single ultimate boundary is misguided. There is no edge, only an infinite branching of possibilities beyond our reach. Observational limitations further constrain our ability to search for cosmic boundaries. Even with the most advanced telescopes, we are still bound by the resolution limits of our instruments, the interference of cosmic dust, and the distortions caused by gravitational lensing. The further we look, the more we must rely on indirect evidence rather than direct observation. Dark matter, for example, has never been directly observed, yet we infer its existence through its gravitational effects. If dark matter is so elusive, how many other hidden structures might exist beyond our current technological reach? Could there be forces, dimensions, or entities operating on a scale so vast that they are beyond even our most ambitious theories? Every time science has attempted to define an ultimate limit, it has been forced to revise its understanding. Once we believed that Earth was the center of the universe. Then we discovered that our Sunday was one of many in a vast galaxy. We later learned that our galaxy was just one among billions, and that the universe itself was expanding. Now, we face the possibility that even our universe is not unique, that we may never find an absolute framework that explains everything. This constant evolution of knowledge suggests that no matter how far we push the boundaries, there will always be something beyond them, an ever-receding horizon of mystery. And so, we must ask ourselves, if there is no final edge, no ultimate answer, does that make our search futile? Or does it make the journey even more meaningful? If the nature of reality is one of infinite complexity, then perhaps our role is not to seek an end, but to continuously expand our understanding, embracing the paradoxes and contradictions that challenge us. The questions we ask today may not be the same questions we ask tomorrow, and each answer will lead to new frontiers of exploration. This is the essence of scientific curiosity, the recognition that while we may never reach the ultimate truth, the act of searching, of questioning, and of pushing the limits of our knowledge is what defines us. Whether or not we ever find the edge of the universe, we will continue to explore, not because we expect a final revelation, but because the unknown itself is the greatest challenge, and within it lies the endless potential for discovery. The search for the true nature of the universe, question of whether it has an edge or extends infinitely, has fueled one of the greatest conflicts in modern cosmology. At the heart of this struggle lies a fundamental tension between competing scientific theories, observational constraints, and the limits of human comprehension. Throughout history, each time scientists believed they had arrived at a complete understanding of the cosmos, new discoveries shattered old assumptions, revealing deeper complexities and paradoxes that forced a re-evaluation of everything thought to be true. Today, the battle to define the boundaries of the universe remains unresolved, with cosmologists divided between those who believe in a finite cosmos with a definable shape and those who argue for an infinite, unbounded expanse with no ultimate edge. The conflict is not just a theoretical one. It is a battle between what we can observe and what mathematical models suggest might exist beyond the limits of our perception. One of the greatest sources of tension arises from the discrepancy between general relativity, which describes the universe on the largest scales, and quantum mechanics, which governs the smallest. Albert Einstein's general theory of relativity provides an elegant framework for understanding cosmic expansion, black holes, and the curvature of space-time, but it breaks down when applied to the extreme conditions at the very beginning of the universe or deep within singularities. Meanwhile, quantum mechanics, which has been extraordinarily successful in describing particle interactions and fundamental forces, cannot yet be reconciled with relativity in a way that produces a complete picture of the universe's structure. This division creates a fundamental uncertainty. If our two most successful physical theories cannot be unified, how can we trust either of them to provide a definitive answer about whether the universe has a finite structure or extends forever? The competing theories about the shape of the universe add another layer of complexity to this scientific struggle. A finite universe, one with a definite size and shape, is supported by models that suggest space could be curved in such a way that traveling far enough in one direction would eventually bring you back to your starting point. This concept, known as a closed universe, implies that space is finite, yet unbounded, much like the surface of a sphere. The idea is deeply compelling because it offers a solution to the paradox of infinity. If the universe is curved back on itself, then it can be vast, yet still measurable. However, this model requires that the universe contain enough matter to gravitationally close it, an idea that has lost favor with the discovery that the universe's expansion is accelerating due to dark energy. The opposite argument is that the universe is infinite, with no boundaries or ultimate edge. This model aligns with observations showing that the large-scale structure of the universe appears flat rather than curved, suggesting that space extends forever in all directions. An infinite universe introduces its own paradoxes, such as the idea that, given enough distance, every possible configuration of matter, including an exact replica of our own galaxy, solar system, and even personal histories, must exist somewhere in the vast expanse. This concept, known as the cosmic doppelganger paradox, is unsettling but mathematically unavoidable in an infinite cosmos. If the universe has no edge, then what we perceive as the observable universe is only a tiny fraction of a never-ending, ever-expanding reality, and we may never be able to reach a definitive conclusion about its full extent. The struggle to determine whether the universe is finite or infinite is further complicated by observational constraints. The most distant light we can observe comes from the cosmic microwave background radiation, CMB, the afterglow of the Big Bang. This ancient light, released when the universe was just 380,000 years old, forms a sort of cosmic horizon, beyond which we cannot see because the early universe was opaque to photons. If there is an edge to the universe, it would lie far beyond this horizon, hidden from direct observation. The expansion of the universe makes this problem even worse. Distant galaxies are moving away from us faster than the speed of light due to the stretching of space itself, meaning that even if an edge exists, it is receding at an accelerating rate and will always remain beyond our reach. Another major point of contention is the nature of dark matter and dark energy, two invisible components that together make up 95% of the universe's total mass energy content. The existence of dark matter was inferred from the unexpected rotation speeds of galaxies, which suggested the presence of an unseen mass holding them together. Dark energy, on the other hand, was discovered through observations of distant supernovae, which showed that the universe's expansion is not slowing down, as originally expected, but accelerating. These two phenomena are deeply tied to the question of the universe's shape and fate. If dark energy continues to dominate, it could lead to a big rip in which the fabric of space-time itself is torn apart, destroying all matter and structure. Alternatively, if dark energy behaves differently over time, it could lead to a cyclic universe, where expansion eventually reverses, leading to a new Big Bang. These opposing outcomes highlight the uncertainty in our understanding. Without knowing the true nature of dark energy, we cannot definitively say whether the universe is infinite or if it will one day collapse. The clash between observable evidence and theoretical models extends even further with the emergence of the multiverse hypothesis, an idea that suggests our universe is just one of many, each existing within a larger cosmic landscape. Some versions of the multiverse theory propose that new universes are constantly being formed in an endless process of cosmic inflation, meaning that the edge of our universe might simply be the boundary where it transitions into another, completely separate universe. If true, this would mean that searching for a finite boundary to our cosmos is fundamentally misguided. The observable universe is not the totality of existence, but merely a small region within an infinitely larger system. However, the multiverse theory remains controversial because, by definition, other universes would be beyond our observational reach, making the theory impossible to test or confirm. Even within our own universe, black holes represent another significant challenge to our understanding of boundaries. The event horizon of a black hole is often described as a point of no return, beyond which nothing, not even light, can escape. In a way, black holes serve as microcosmic examples of the problem cosmologists face when trying to define an ultimate edge to the universe. If something falls into a black hole, is it truly lost forever, or does its information persist in some form? The famous black hole information paradox arises from this question, as quantum mechanics suggests that information cannot be destroyed. Yet general relativity predicts that anything crossing the event horizon is effectively erased from the universe. If we cannot resolve the paradox of an edge within a single black hole, how can we hope to determine whether the entire universe has a boundary? Ultimately, the conflict surrounding the edge of the universe is not just about scientific theory, as it is about the nature of human understanding itself. Each time we develop a new model to explain the cosmos, new paradoxes emerge, challenging our assumptions and forcing us to question the limits of our perception. Are we equipped, both intellectually and technologically, to ever find a definitive answer? Or will the true nature of the universe forever elude us, slipping further from our grasp each time we think we are close? The struggle to define the cosmos is not just a battle between competing theories, but a reflection of our deepest existential questions. What is reality? Is there an end to everything? Or does existence stretch infinitely? Is our universe a singular creation, or are we part of a much larger, unknowable multiverse? The answers remain uncertain, but the search itself is what drives science forward. Whether the universe is finite or infinite, whether it has an edge or not, the conflict between theories is a testament to humanity's relentless pursuit of knowledge. Each observation, each mathematical equation, each new telescope launched into the void brings us one step closer, even if the destination is forever just beyond our reach. If the universe has no edge, if it extends infinitely in all directions, with no ultimate boundary, the consequences for physics, cosmology, and even philosophy are profound. The idea of an infinite universe fundamentally alters our understanding of space, time, and existence itself. It challenges the very nature of scientific inquiry, forcing us to reconsider whether we can ever achieve a complete understanding of reality. It raises questions about our place in the cosmos, about the meaning of our existence within an endless expanse, and about the limitations of human perception when faced with something that has no definable end. If there is no edge, then what does that mean for the fundamental laws of physics? Can a universe without boundaries ever be fully understood? Or are we chasing an answer that will always remain just beyond our grasp? The consequences of such a realization ripple through every aspect of scientific thought, stretching from the equations that govern the behavior of galaxies to the deepest philosophical questions about the nature of infinity. One of the most immediate consequences of an infinite universe is the impact it has on cosmological models. The current leading theory of cosmology, the Big Bang model, suggests that the universe began as a singularity, an infinitely small, hot, and dense point that rapidly expanded to form the vast cosmos we see today. However, if the universe is truly infinite, this raises an important question. Was it always infinite, even at the moment of the Big Bang? If so, then what exactly was expanding? The traditional image of a balloon inflating does not apply if the universe had no finite size to begin with. This forces a reconsideration of the very nature of expansion, rather than space growing into something. It may be that the metric that defines distances between objects is changing. In an infinite universe, the concept of an origin point becomes much harder to define, challenging the notion that the cosmos had a definite beginning in the way we typically think of beginnings. The implications for physics go even deeper. If the universe is infinite, then the laws of physics as we know them might not be the same everywhere. We assume that the fundamental constants, such as the speed of light, the charge of an electron, or the strength of gravity are universal, applying equally to every region of space. But in an infinite cosmos, is that assumption justified? What if there are regions where the laws of physics are different? The idea that the universe might be infinite brings with it the possibility of what physicists call the cosmic landscape, a multiverse-like scenario in which different regions of space have different physical constants. This could explain why our universe seems so finely tuned. For life, perhaps, we exist in one of many infinite regions, each with different properties, and only the ones that allow for complex structures like galaxies, stars, and biological life develop in a way that can be observed. The implications of an infinite universe also touch on the problem of determinism in physics. In a finite universe, it is theoretically possible to map out all known particles and predict their evolution over time. But in an infinite universe, where there is no upper limit to the amount of matter and energy, predictions become meaningless beyond a certain scale. This fundamentally challenges the idea of predictability in physics. If everything that can happen has already happened an infinite number of times somewhere else, does that mean the future is already written? Or does it mean that no true predictions can ever be made? Perhaps one of the most bizarre consequences of an infinite universe is the idea that, given infinite space, every possible arrangement of matter must exist somewhere. This means that there could be copies of our galaxy, our solar system, and even ourselves scattered throughout the cosmos. The idea of infinite cosmic doppelgangers is not a philosophical abstraction. It is a direct mathematical result of an unbounded universe with a finite set of possible physical configurations. If there are only so many ways atoms can be arranged, then an infinite universe must eventually repeat itself. This means that somewhere out there is another version of you, living a life identical in every way to your own, yet slightly different in others. Perhaps in some of these duplicate universes, you made different choices, took a different job, said something you regretted, lived a completely different life. The implications of this are staggering. If there are infinite copies of you, what does that say about free will? Are our choices truly our own? Or are they simply variations playing out across an infinite number of realities? This naturally leads to profound existential questions. If the universe has no edge, if it is infinite in both space and time, then what does that mean for the concept of purpose? Throughout history, many human belief systems have been built around the idea of a finite world, a structured cosmos with a clear order and a guiding force. An infinite universe, however, offers no such structure. It has no center, no boundary, no preferred location. We are not at the heart of anything. We are merely one speck in an endless ocean of existence. For some, this idea is deeply unsettling. It suggests that we are not special, that our lives, our struggles, our triumphs are all insignificant on a cosmic scale. If civilizations rise and fall in an infinite loop, if entire galaxies are born and destroyed endlessly, does anything truly matter? Yet, paradoxically, an infinite universe can also be seen as liberating. If existence is infinite, then the possibilities are limitless. There will always be more to discover, more to explore, more questions to ask. The idea that the universe has no edge means that human curiosity has no boundary. There will never be a final answer, never a moment when we have learned everything there is to know. Every discovery leads to new mysteries, ensuring that the pursuit of knowledge is an eternal process. In this way, the realization that the universe is boundless does not diminish our significance. It enhances it, making our role as explorers, scientists, and thinkers more important than ever. The realization that we may never find a final edge also signals the need for new physics beyond our current models. The standard model of particle physics, which describes the behavior of fundamental particles, has been incredibly successful, but remains incomplete. It cannot account for dark matter, dark energy, or the force of gravity at quantum scales. General relativity, while a masterful description of gravity, breaks down in extreme conditions, such as black hole singularities and the Big Bang. If the universe is truly infinite, then both of these theories must be expanded to accommodate new possibilities, perhaps through a quantum theory of gravity, a new understanding of space-time, or even a complete restructuring of how we think about physical laws. Some theories suggest that space itself may not be fundamental but emergent, arising from deeper, unknown principles. Others propose that time is an illusion, that what we perceive as past, present, and future are merely different slices of a higher dimensional structure. If these ideas are correct, then the very framework of physics must change. The search for a final, complete theory of everything, a single equation that explains all forces and phenomena, may itself be an illusion. If the universe has no edge, then perhaps physics itself has no final limit. Every time we think we have reached the ultimate explanation, new questions will emerge, forcing us to rethink our most fundamental assumptions. This is the true consequence of an infinite universe. It is not just a physical or mathematical challenge, but a conceptual one. It forces us to accept that knowledge is never absolute, that discovery is never ending, and that reality itself may be something far stranger than we can currently imagine. Ultimately, whether we accept it with dread or awe, an infinite universe forces us to redefine not only physics and cosmology, but also our place within it. It challenges us to embrace uncertainty, to push beyond the boundaries of what we think we know, and to continue searching for answers, even if those answers only lead to greater mysteries. In the grand cosmic expanse, where the edge may never be found, the journey of discovery itself becomes the greatest adventure. The quest to understand the cosmos has been marked by moments of profound revelation, turning points that have fundamentally altered our perception of reality. Throughout history, each breakthrough in astronomy and physics has forced scientists to reconsider long-held beliefs, often replacing certainty with deeper, more complex mysteries. The discoveries of general relativity, quantum mechanics, and cosmic expansion were not just scientific milestones. They were paradigm shifts that changed humanity's place in the universe. And now, in the modern era, we stand at the edge of another such turning point, where the discovery of dark energy, the acceleration of cosmic expansion, and the development of revolutionary technology are reshaping our understanding of everything from the fate of the universe to the nature of space-time itself. What we thought was a universe governed by predictable laws has revealed itself to be a dynamic and unpredictable system, one that challenges even our most fundamental assumptions about the fabric of reality. Perhaps the most significant revelation in modern cosmology is the discovery that the universe is not just expanding, but accelerating outward due to an unknown force dubbed dark energy. This finding, first confirmed in the late 1990s by two independent teams studying distant supernovae, shattered the long-standing belief that gravity would eventually slow the expansion of the universe. The expectation was that, after the Big Bang, the universe would either expand forever, at a decreasing rate, or eventually contract under the pull of gravity. Instead, observations revealed that galaxies were receding from each other at an increasing rate, meaning that some unknown force was overcoming gravity itself. This discovery earned the 2011 Nobel Prize in Physics. But more importantly, it introduced one of the greatest mysteries in science: what is dark energy? And why is it causing the universe to expand at an ever-increasing pace? Dark energy makes up an estimated 68% of the total energy content of the universe, yet we know almost nothing about it. One prevailing hypothesis is that dark energy is related to the cosmological constant, a term originally introduced by Albert Einstein in his equations of general relativity. Einstein initially considered the cosmological constant to be a mathematical trick to keep the universe static. But when the expansion of the universe was discovered, he abandoned it, calling it his greatest blunder. Ironically, modern observations suggest that some version of the cosmological constant may be real, describing a vacuum energy inherent in space itself. If this is true, it means that empty space is not truly empty, but is filled with an energy field that exerts a repulsive force, driving galaxies apart. Another possibility is that dark energy is not a constant force, but an evolving one, changing in strength over time. If this is the case, then our predictions about the fate of the universe may be incorrect. In some models, dark energy could grow so powerful that it eventually tears apart galaxies, stars, planets, and even atoms, in a hypothetical scenario known as the Big Rip. In others, dark energy might decay, reversing the expansion and leading to a future where the universe collapses back into a singularity, a big crunch. There is also the possibility that dark energy fluctuates, leading to an endless cycle of expansion and contraction, giving rise to a big bounce where new universes are born from the remnants of previous ones. Each of these scenarios presents a radically different view of the ultimate destiny of the cosmos. Yet without understanding the true nature of dark energy, we cannot say which, if any, is correct. Technological advancements have played a crucial role in bringing us to this turning point, pushing the boundaries of what we can observe and measure. One of the greatest tools in this pursuit has been space telescopes, which allow us to peer deeper into the universe than ever before. The Hubble Space Telescope, launched in 1990, revolutionized astronomy by providing high-resolution images of galaxies, nebulae, and deep space phenomena, leading to countless discoveries, including the precise measurement of the expansion rate of the universe. More recently, the James Webb Space Telescope, JWST, has taken our observational capabilities even further, using infrared vision to see through cosmic dust and examine the earliest galaxies formed after the Big Bang. Webb's ability to analyze the atmospheres of exoplanets has opened new possibilities in the search for life beyond Earth, allowing scientists to detect potential biosignatures such as oxygen, methane, and water vapor on distant worlds. Other groundbreaking observatories, such as the European Space Agency's Euclid Telescope and NASA's Nancy Grace Roman Space Telescope, are now being developed to study the large-scale structure of the universe and map the distribution of dark matter and dark energy with unprecedented precision. These instruments are designed to answer fundamental questions about the nature of cosmic acceleration, providing insights into whether dark energy behaves as a constant force or if it evolves over time. By studying the clustering of galaxies, the bending of light through gravitational lensing, and the cosmic microwave background radiation, these missions may bring us closer to solving one of the greatest mysteries of all time. Beyond telescopes, new experimental techniques are pushing the limits of physics itself. The Laser Interferometer Gravitational Wave Observatory, LIGO, and its European counterpart, Virgo, have detected gravitational wave ripples in space-time caused by massive cosmic events such as black hole mergers. These detections confirm a key prediction of Einstein's relativity and provide a completely new way to observe the universe, allowing us to, for centuries, humanity has tried to piece together the puzzle of the universe using the framework of classical physics, general relativity, and quantum mechanics. Yet with every step forward, new paradoxes emerge. Perhaps we are asking the wrong questions, Or perhaps we are looking at the problem from the wrong perspective altogether. What if our traditional understanding of space, time, and cosmic structure is fundamentally flawed? As our ability to observe and analyze the universe advances, alternative theories are beginning to reshape scientific discussions, challenging long-standing assumptions about the nature of reality. Among these revolutionary ideas is the holographic principle, a concept that suggests our three-dimensional universe may be nothing more than a projection of information encoded on a distant two-dimensional surface. If true, this would upend everything we think we know about existence, changing not only our understanding of the cosmos, but also our place within it. The holographic principle emerged from the study of black holes, specifically the way information behaves at their event horizons. In classical physics, information about an object that falls into a black hole is thought to be lost forever, violating the principles of quantum mechanics, which state that information cannot be destroyed. However, physicists such as Jacob Bekenstein and Stephen Hawking discovered that black holes emit a faint radiation now called Hawking radiation, which suggests that information may be preserved in some form. This led to the realization that the information content of a black hole is not stored within its volume, but rather on its surface, much like a hologram. The implications of this discovery were staggering. If black holes store information holographically, could the entire universe operate on the same principle? Could our perception of three-dimensional space be an illusion, a projection of deeper, fundamental data encoded on the fabric of the cosmos itself? The idea that the universe may be fundamentally two-dimensional, with everything we experience emerging from a distant, underlying layer of information, is not as far-fetched as it sounds. In fact, string theory, a leading candidate for a theory of everything, supports this notion. String theory posits that all matter and energy are composed of tiny vibrating strings existing in multiple dimensions, but it also suggests that space-time itself may be an emergent phenomenon rather than a fundamental aspect of reality. This would mean that the fabric of the universe, including gravity, emerges from something even deeper, possibly quantum information encoded in a lower dimensional reality. In this view, the edge of the universe may not be a physical boundary in the way we imagine, but rather a limitation in how information is structured and perceived. We may be like characters in a simulation, experiencing a projected reality without direct access to the deeper computational substrate that generates it. This shift in perspective dramatically alters the way we think about cosmic structure, particularly regarding the supposed contradictions between quantum mechanics and general relativity. Traditionally, the two theories have been at odds. Relativity describes the universe on the grandest scales, treating space-time as a smooth continuum, while quantum mechanics governs the smallest scales, where uncertainty and probability dominate. Attempts to unify them have led to paradoxes, such as the incompatibility of space-time singularities with quantum theory. However, if space-time itself is emergent, then these paradoxes may be an illusion. Just as an image projected on a screen can appear three-dimensional while actually being two-dimensional, our perception of deep space and infinite distance may be a result of our limited perspective. Another alternative viewpoint that is reshaping scientific discussions is the idea that time itself may not be fundamental. In classical physics, time is treated as a separate dimension, flowing in one direction from past to future. But in quantum mechanics, time behaves very differently at the smallest scales. Particles do not follow a strict past-to-future trajectory, but instead exist in a superposition of possible states, where time is not a fixed parameter, but an aspect of probability distributions. Some physicists, such as Carlo Rovelli, argue that time is an emergent phenomenon arising from the way quantum systems interact with one another. If this is true, then the universe's beginning and end may not be meaningful concepts in the way we currently think of them. Instead of searching for a distinct origin or edge to the universe, we may need to rethink causality itself, viewing the cosmos as a web of interconnected information rather than a timeline with a defined start and finish. The role of quantum mechanics in cosmic structure becomes even more apparent when considering the possibility that the universe itself is a quantum system. Quantum entanglement, the phenomenon where particles remain connected regardless of distance, suggests that space-time is more interconnected than classical physics allows. Recent research has proposed that space-time may actually be woven together by networks of entangled quantum states, meaning that what we perceive as space is a manifestation of deeper, underlying quantum relationships. If this is true, then the edge of the universe may not be a physical barrier, but rather a threshold, where entanglement patterns break down or transition into another form of reality. These alternative theories force us to reconsider how we interpret scientific data. If the universe is holographic, if space-time is emergent, if time is not fundamental, then many of the paradoxes that arise in cosmology may be resolved by changing the way we look at them. The question of whether the universe has an edge may be meaningless if space itself is a projection of deeper quantum structures. The contradictions between relativity and quantum mechanics may disappear if both are seen as approximations of a more fundamental information-based reality. Instead of searching for the end of the universe in a physical sense, we may need to look for the limits of information processing within the cosmic fabric. Changing our perspective in this way does not diminish the importance of scientific exploration. If anything, it makes the search for truth even more exciting. The realization that we may be thinking about the universe in the wrong way does not mean we are lost. It means we are on the verge of a deeper understanding. Throughout history, major scientific revolutions have occurred when thinkers abandoned outdated assumptions and embraced radically new ideas. The transition from a geocentric to a heliocentric model of the solar system, the discovery of relativity, the development of quantum mechanics, each of these moments required a fundamental shift in how we viewed reality. We may now be standing on the brink of another such shift, where the nature of space, time, and information itself is being redefined. As our understanding of the universe evolves, so too must our willingness to accept ideas that challenge intuition. If we can accept that space and time are not fundamental, that the universe may be a projection of deeper structures, and that reality itself may be shaped by quantum relationships beyond our comprehension, then we open the door to new possibilities that could finally bridge the gap between our current theories and the hidden truths of the cosmos. Perhaps the universe does not have an edge in the way we expect, because we have been looking at the problem from within a limited framework. By shifting our perspective, we may come closer to uncovering the real nature of existence, not as an expanding three-dimensional space, but as something far stranger, more intricate, and more interconnected than we ever imagined. For centuries, human curiosity has driven us to explore, analyze, and attempt to define the universe we inhabit. Every breakthrough, every discovery of a new law, force, or cosmic structure has seemed to bring us closer to an ultimate truth. And yet, just when it feels like we have a firm grasp on reality, the universe throws an unexpected twist, defying our past assumptions and reshaping our understanding of existence itself. What if everything we thought we knew about space, time, and reality was only scratching the surface of something far more complex? What if, instead of a singular universe governed by clear-cut physical laws, we exist within an endless web of possibilities, where reality is shaped not by deterministic rules but by probabilities, simulations, and unseen dimensions? The more we explore, the more we realize that the nature of the cosmos is not just vast, it is fundamentally strange, and perhaps beyond what the human mind was ever designed to comprehend. One of the most radical shifts in modern physics comes from the multiverse theories, which suggest that our universe may not be the only one. For centuries, we have assumed that the cosmos we observe, the one governed by general relativity and quantum mechanics, is the totality of existence. However, as our understanding of quantum physics and cosmic inflation deepens, new models suggest that our universe may be just one of an infinite number, each with its own set of physical laws, constants, and even different dimensions of space and time. If this is true, then our attempts to find a single, unified theory of everything may be doomed to failure, not because our methods are flawed, but because no single theory could ever encapsulate the infinite variations of reality that might exist. The eternal inflation model, proposed by physicist Alan Guth, provides one of the strongest frameworks for the multiverse concept. According to this model, the rapid inflation that occurred during the first moments after the Big Bang did not happen uniformly across all regions of space. Instead, Different patches of the universe may have experienced inflation at different rates, creating bubbles of reality, each forming its own separate universe with unique physical properties. In this scenario, our observable universe is just one such bubble, floating in a vast cosmic foam of other universes, each inaccessible to us due to the infinite separation caused by ongoing inflation. If this is true, then fundamental aspects of our reality, such as the strength of gravity, the charge of the electron, or even the number of spatial dimensions, could be mere accidents of our particular bubble, rather than universal constants. Somewhere out there, in another universe, physics itself could operate in a way that is completely alien to us. Even more unsettling is the possibility that these parallel universes could contain alternate versions of ourselves. If reality is truly infinite, then every possible arrangement of matter must exist somewhere, meaning that there could be exact duplicates of our own world, our own history, and even our own consciousness scattered throughout the multiverse. This concept, known as quantum branching or the many worlds interpretation, suggests that every quantum decision results in the splitting of reality, creating countless versions of the universe in which different outcomes play out. If this is true, then every choice you have ever made, every decision, every moment exists in multiple forms, playing out in different versions of reality. Somewhere, another version of you is reading this, but with a different set of thoughts, experiences, or even a different past leading up to this moment. If this is the true nature of existence, then what does it mean to be an individual? Is you defined only by the particular universe you occupy? Or are you an infinite set of possibilities, existing in countless variations across the multiverse? But perhaps the most mind-bending twist of all is the growing consideration that the universe itself might not be real in the way we traditionally understand it. The simulation hypothesis, proposed by philosopher Nick Bostrom, suggests that our reality may be nothing more than an advanced computational construct, a simulated existence running on an immense processing system beyond our comprehension. While this idea might sound like science fiction, some of the greatest minds in physics and technology, including Elon Musk and Neil deGrasse Tyson, have seriously considered its implications. If a civilization were advanced enough to simulate conscious beings, how would those beings ever be able to tell the difference between reality and simulation? If our universe operates according to strict mathematical rules, if every particle interaction, every law of physics, and even the speed of light itself are merely constraints within a larger computational framework, then we may be nothing more than digital consciousness running on an incomprehensibly complex system. Some physicists argue that hints of a simulated reality may already exist in the fundamental structure of the universe. Quantum mechanics, for instance, suggests that particles only take definite states when observed, as if reality does not render itself until it is being actively measured. This bizarre property, known as wave function collapse, has puzzled scientists for decades. Why would the universe behave this way, unless observation itself was a fundamental part of its design? Additionally, the discovery that the universe operates on a finite amount of information, similar to how digital computers store data, raises the question of whether reality itself is simply a vast computation running at the smallest possible scales. But if we are living in a simulation, who or what created it? Is our universe the result of an advanced civilization running a simulation of its own past, studying the behavior of intelligent beings? Or are we part of a nested system where simulated beings eventually develop their own simulations, creating a fractal chain of realities stretching infinitely downward? The implications of this idea are staggering. If we are simulated, does that mean we have no free will? Or could it be that the simulators themselves are part of a simulation, unaware that their own reality is artificial? The deeper one explores the simulation hypothesis. The more it challenges everything we assume about existence. And yet, despite these radical ideas, a deeper realization emerges: perhaps it does not matter whether the universe is infinite, one of many, or a grand simulation. Our experience of it remains the same. We still feel, think, explore, and create. We still experience love, curiosity, ambition, and wonder. If we are simulated beings, we are still real, in the sense that we perceive reality, we form relationships, and we seek meaning. If the universe has no edge, it does not diminish the fact that we have the ability to contemplate it. If parallel versions of ourselves exist, it does not change the choices we make in this particular moment. In the grandest cosmic sense, perhaps the greatest twist of all is that, despite the infinite complexity of the universe, our personal experiences, emotions, and connections remain deeply meaningful. As scientific discoveries continue to challenge our assumptions, we are faced with an extraordinary realization. We may never find a final answer. Every new discovery leads to deeper questions, and every attempt to define reality reveals layers of complexity that push beyond our understanding. But maybe that is the beauty of it all. The universe, in all its mysteries, invites us not to find a simple answer, but to embrace the search itself. We are explorers, not just of space, but of ideas, of possibilities, of truths beyond what we currently comprehend. The greatest twist is not that the universe defies our expectation set, is that we continue to seek, despite knowing that the journey itself may be infinite. And perhaps, in the end, that is the truest purpose of all. As we stand on the frontier of modern cosmology, each groundbreaking discovery brings with it a cascade of new challenges, unanswered questions, and unresolved paradoxes. Despite the immense progress we have made in understanding the cosmos, from mapping the large-scale structure of the universe to detecting gravitational wave-significant hurdles, remain. Some of these challenges stem from the limitations of our current observational technology, while others arise from the theoretical gaps that persist between quantum mechanics, general relativity, and the unknown nature of dark matter and dark energy. The need for next-generation space missions has never been greater. As scientists push beyond the boundaries of what we currently know, seeking answers to questions that could redefine our understanding of existence itself. One of the greatest obstacles facing cosmologists today is the inability to directly observe the earliest moments of the universe. The Big Bang Theory provides a well-supported model for the early expansion of the cosmos, but we lack direct observational data from the first few moments after its inception. The cosmic microwave background, CMB, the faint radiation left over from roughly 380,000 years after the Big Bang, provides a crucial window into the universe's infancy. Yet it does not tell us what happened before that time. In particular, the Planck epoch, the period within the first 10, circumflex -43 seconds after the Big Bang, remains a mystery because our current understanding of physics breaks down at these scales. Without a working theory of quantum gravity, we are unable to describe what occurred during this crucial moment. Did the universe emerge from a singularity, or was it the result of a quantum fluctuation from a previous cosmic state? Did time itself begin at this moment, or is time an emergent phenomenon from a deeper, unknown reality? Answering these questions will require new physics beyond the standard model. A major limitation facing observational cosmology is the nature of dark matter and dark energy, of the most significant and yet poorly understood components of the universe. Together, these unseen forces account for roughly 95% of the universe's total mass energy content, yet they have never been directly observed. Scientists infer the presence of dark matter through its gravitational effects on galaxies. But despite decades of searching, no experiment has successfully detected a dark matter particle. If dark matter consists of weakly interacting massive particles, WIMPs, as many theories suggest, then our detectors should have found them by now. The failure to do so has led to growing interest in alternative explanations, such as axions, sterile neutrinos, or even modifications to gravity itself. Similarly, dark energy remains an even greater mystery. We know it is causing the expansion of the universe to accelerate, but we do not know why. Is dark energy a property of space itself, as described by Einstein's cosmological constant? Or is it a sign of a new, undiscovered force acting on cosmic scales? Without a clearer understanding of these invisible influences, we are left with a fundamental gap in our knowledge of how the universe operates. Another challenge is the resolution limit of current telescopes, which prevents us from observing the most distant galaxies in sufficient detail to understand their formation. Even with the James Webb Space Telescope, JWST, which has revolutionized infrared astronomy, we are still limited by the sensitivity of our instruments. As light travels from the most ancient galaxies, it becomes redshifted due to the expansion of the universe. meaning that detecting the earliest cosmic structures requires ever more advanced technologies. The next generation of space observatories, such as the European Space Agency's Euclid Telescope and NASA's Nancy Grace Roman Space Telescope, will provide deeper insights into dark matter distribution and the large-scale cosmic web, but they will still be constrained by the fundamental challenge of looking back in time through a universe that has evolved over billions of years. Even if we detect the first galaxies, can we ever hope to observe the conditions before galaxies existed? What was the universe like before stars, before atoms even formed? One possible solution is the development of next-generation cosmic background detectors, capable of measuring not just the cosmic microwave background but also earlier forms of radiation, such as the cosmic neutrino background. If we could detect these primordial neutrinos, which were released just seconds after the Big Bang, we could peer deeper into the early universe than ever before. Future missions like CMBS-4, a proposed ground-based observatory for studying the polarization of the cosmic microwave background, could help refine our understanding of inflation if it occurred, how it occurred, and whether it left detectable imprints on space-time. A related challenge is the growing need for quantum gravity research, a theory that successfully merges general relativity and quantum mechanics. Currently, these two foundational theories of physics are mathematically incompatible, leading to paradoxes in extreme environments such as black holes and the early universe. The leading candidate for a quantum theory of gravity is string theory, which suggests that space-time is composed of tiny vibrating strings at scales far smaller than what can currently be observed. Another promising approach is loop quantum gravity, which attempts to quantize space-time itself into discrete units. While these theories provide fascinating possibilities, neither has yet produced experimental evidence. Testing quantum gravity will require new kinds of experiments, possibly using high-energy particle accelerators or observing gravitational waves from colliding black holes to detect subtle quantum effects. Beyond theoretical and observational challenges, the sheer scale of space poses another obstacle. How do we explore regions of the universe that are inaccessible with current propulsion technologies? The observable universe is 93 billion light-years across, but even within our own galaxy, reaching the nearest stars would take thousands of years with today's fastest spacecraft. If we are to directly study exoplanets for signs of life or probe the interstellar medium beyond our solar system, we will need propulsion technologies that far exceed our current capabilities. Concepts such as light sails, which use laser beams to push ultralight probes to a fraction of the speed of light, have been proposed as a means to reach neighboring star systems like Alpha Centauri within a human lifetime. Other speculative ideas, such as warp drives and quantum teleportation, remain in the realm of science fiction, but highlight the need for radically new approaches to interstellar travel if we are ever to physically explore the universe beyond our solar neighborhood. Another fundamental challenge is the issue of cosmic censorship, the idea that certain aspects of the universe may be permanently hidden from us. If the universe is truly infinite, or if multiverse theories are correct, then there may be entire regions of reality that we can never access, no matter how advanced our technology becomes. Some aspects of physics suggest that information may be fundamentally unknowable beyond certain horizons, such as inside black holes or beyond the observable universe. If information is lost in these regions, are we limited to only partial knowledge of the cosmos? Could there be phenomena so deeply buried behind event horizons or in parallel dimensions that they will forever remain beyond our reach? Despite these formidable challenges, scientists are developing innovative ways to tackle the unanswered questions of the universe. The construction of next-generation particle accelerators, such as the proposed Future Circular Collider, FCC, and the International Linear Collider, aims to probe energies higher than those accessible at the Large Hadron Collider, LHC, potentially uncovering new particles that could explain dark matter or hint at deeper fundamental forces. Upcoming gravitational wave observatories, such as the Laser Interferometer Space Antenna, LISA, will allow us to detect ripples in space-time from cosmic events that occurred billions of years ago, possibly revealing new insights into black holes, neutron star mergers, and exotic remnants of the early universe. Meanwhile, artificial intelligence and machine learning are playing an increasingly crucial role in analyzing the vast amounts of data collected by telescopes and experiments. The amount of astronomical data is so immense that human researchers alone cannot process it all. But AI algorithms are capable of identifying patterns, anomalies, and previously undetected phenomena at unprecedented speeds. This technological revolution could lead to new discoveries that humans might otherwise overlook. Ultimately, the next steps in our cosmic journey will depend on a combination of improved observational tools, theoretical breakthroughs, and technological innovations that push beyond the limits of what we currently believe is possible. Each unanswered question serves as an invitation and opportunity to expand our knowledge, challenge our assumptions, and redefine the boundaries of human understanding. The greatest mysteries of the universe remain unsolved. But with every challenge comes the potential for new discoveries that will once again reshape our perception of reality. The universe is still speaking to us in riddles, and it is up to us to continue listening. The quest to understand the universe has brought us to the final frontier of knowledge, where the greatest minds in physics are engaged in an ongoing battle to define the fundamental nature of reality. At the heart of this confrontation lies the conflict between competing theories, each offering different explanations for the cosmos, but none fully resolving the mysteries that haunt modern physics. The debate rages on. Is the universe infinite, or does it have a boundary we will one day uncover? Can we ever hope to unify general relativity and quantum mechanics into a single theory that explains everything? And what does the future of cosmology hold as we stand at the precipice of discovery, facing questions that will determine the fate of physics itself? The latest competing theories and their strengths. Several leading theories currently dominate the conversation about the structure and fate of the universe. Each has its strengths, yet none has emerged as the definitive answer to the greatest questions in cosmology: the infinite universe model. This theory suggests that the universe has no edge and extends infinitely in all directions. Observations of the large-scale structure of the universe suggest that space is flat rather than curved, implying that it could stretch forever. If true, this would mean that every possible configuration of matter exists somewhere in the cosmos, including infinite versions of our own galaxy, solar system, and even alternate versions of ourselves. The strength of this theory lies in its compatibility with inflationary cosmology, which suggests that the rapid expansion following the Big Bang could have created an unbounded, ever-growing universe. The finite universe with a boundary. Some models propose that the universe is finite but unbounded, much like the surface of a sphere. In this view, traveling far enough in one direction would eventually bring you back to where you started, much like how a person walking on Earth never encounters an edge. This model avoids the paradoxes associated with an infinite universe, while remaining consistent with general relativity. However, if the universe is finite, the question remains: what lies beyond its boundary? Is there a higher dimensional space in which our universe is embedded, or does the concept of beyond have no meaning? The cyclic universe and Big Bounce theories. Instead of a singular Big Bang, some theories propose that the universe undergoes infinite cycles of expansion and contraction. This means that instead of having a distinct beginning, the universe could be reborn from a previous collapsed state. String theory supports this idea through the concept of brane collisions in higher dimensional space, where multiple universes could interact, creating cycles of destruction and rebirth. If true, this would imply that the universe has no ultimate boundary in time, only endless repetition. The multiverse hypothesis. One of the most radical ideas is that our universe is just one of many, each existing in an enormous cosmic landscape. Some versions of the multiverse arise from eternal inflation, where different regions of space expand at different rates, forming isolated pocket universes with unique physical laws. Others emerge from quantum mechanics, where every quantum event creates branching timelines, forming an infinite tree of parallel realities. The multiverse hypothesis explains why our universe appears so finely tuned for life. It is simply one of countless universes, and we exist in one where the conditions allow for our existence. However, the biggest challenge facing this theory is the lack of testability. If other universes are completely inaccessible, can science ever prove their existence? The holographic universe. Emerging from string theory and black hole physics, the holographic principle suggests that all of the information in our universe may be encoded on a lower dimensional surface, much like a hologram. If this is true, then space and time, as we perceive them, are emergent properties, not fundamental aspects of reality. This theory resolves some paradoxes in black hole physics and quantum mechanics, but it radically changes our understanding of what the universe actually is. The ongoing debate: will we ever find a true boundary? One of the most profound questions in physics is whether the universe has a true edge, either in space or in time. If the universe is infinite, then the quest for an ultimate boundary may be meaningless. However, if the universe is finite, it raises the question, what lies beyond? Some physicists argue that asking what is outside the universe is like asking what is north of the North Pole. The question itself may not have a meaningful answer. Another fundamental issue is whether our observational limits, such as the cosmic horizon, represent an actual boundary, or simply the limits of what we can currently detect. Because the universe is expanding, some regions of space are moving away from us faster than the speed of light, meaning their light will never reach us. These regions exist, but they are permanently beyond our observational reach. If new physics allows us to probe beyond these limits, we may one day answer the question definitively. But for now, it remains open. Unifying physics, the bridge between relativity and quantum mechanics. The ultimate challenge in modern physics is finding a theory that unifies general relativity, which describes gravity on cosmic scales, with quantum mechanics, which governs the behavior of subatomic particles. Currently, these two frameworks are incompatible. Relativity treats space-time as a smooth continuum, while quantum mechanics suggests that reality is fundamentally uncertain and governed by probability. Several attempts to unify these theories are being explored. String theory. String theory proposes that the fundamental building blocks of the universe are tiny, vibrating strings rather than point-like particles. These strings exist in multiple dimensions beyond the familiar three of space and one of time. If correct, string theory could unify all forces of nature, including gravity, into a single framework. However, it remains largely theoretical, as direct experimental evidence is lacking. Loop quantum gravity. This approach suggests that space-time itself is quantized, composed of tiny loops that create a discrete structure. This theory avoids the infinities that plague quantum gravity calculations and provides a possible explanation for what happens inside black holes and at the moment of the Big Bang. Emergent gravity. Some physicists, such as Eric Verlinde, propose that gravity is not a fundamental force, but an emergent property of space-time, similar to how temperature emerges from molecular motion. This could explain why gravity behaves differently on cosmic and quantum scales and provide new insights into the nature of dark matter and dark energy. The future of cosmology. As we look to the future, several breakthroughs could bring us closer to resolving these grand debates. Next-generation observatories. The upcoming James Webb Space Telescope, Euclid, and LISA, Laser Interferometer Space Antenna, will allow scientists to probe deeper into space and detect gravitational waves from the early universe. These instruments may reveal new details about dark energy, dark matter, and the first moments of cosmic inflation. Advances in quantum computing. Quantum computers have the potential to simulate complex quantum interactions that are currently beyond our computational capabilities. This could provide insights into quantum gravity and help test theories that unify the forces of nature. Artificial intelligence in cosmology. Machine learning is playing an increasing role in analyzing massive datasets from telescopes, accelerating discoveries that would take decades using traditional methods. AI may be the key to identifying hidden patterns in cosmic structure and revealing new laws of physics. Breakthroughs in theoretical physics. Theoretical physicists continue to develop new models, many of which challenge our traditional notions of time, space, and causality. Concepts such as retrocausality, where the future influences the past, and non-locality, where quantum effects span vast distances, could reshape our understanding of reality itself. Conclusion. The final confrontation in cosmology is not just a battle between competing theories, but a confrontation with the limits of human knowledge itself. Each new discovery pushes the boundaries of what we thought was possible, yet each answer raises even deeper questions. Will we ever find the true edge of the universe? Or will it always remain just beyond our reach? Will we unify physics into a single, elegant theory? Or will reality forever elude complete comprehension? The search for answers continues, but one thing is certain: The universe, in all its vastness and mystery, is far stranger and more beautiful than we ever imagined. The pursuit of understanding the universe is more than just a scientific endeavor. It is a reflection of humanity's deepest desires, fears, and aspirations. Throughout history, our relentless curiosity has driven us to explore the unknown, to push beyond the boundaries of what is familiar, and to seek answers to questions that, at times, seem impossible to answer. The universe itself serves as a metaphor for the human condition. Vast, mysterious, and filled with both awe, inspiring beauty, and unfathomable challenges. In the end, the moral takeaway from our cosmic journey is not merely about uncovering facts, but about embracing the delicate balance between knowledge and mystery, recognizing that some answers may remain elusive, and finding meaning in the pursuit itself rather than in the final destination. The deeper meaning of exploring the unknown. From the first time early humans looked up at the night sky, they have seen more than just points of light. They have seen a canvas for their imagination, a realm of gods, myths, and untold stories. As our understanding of astronomy has evolved, so too has our relationship with the cosmos. What was once attributed to divine beings, or celestial magic, is now understood through physics and mathematics. Yet the sense of wonder remains. Each time we unlock a new mystery, we are confronted with even greater ones, reminding us that no matter how much we learn, the universe will always be larger than our comprehension. This endless pursuit of knowledge is a testament to the unique nature of human intelligence. Unlike other species, we are not content with survival alone. We seek meaning, purpose, and a deeper understanding of our place in the cosmos. The very act of questioning, why are we here? How did the universe begin? What is beyond the visible horizon? Is what defines us. In this way, the exploration of the unknown is not just about science, but about what it means to be human. It is a reminder that we are part of something far greater than ourselves, and yet within us lies the ability to understand and appreciate that vastness. How curiosity drives scientific progress. The universe is indifferent to our existence, yet we refuse to accept ignorance as our fate. Time and again, human curiosity has propelled us to uncover truths that seemed beyond our reach. Without curiosity, we would have never developed the scientific method, never questioned the motion of the stars, never sought to understand the forces that govern nature. It was curiosity that led Copernicus to challenge the geocentric model of the universe, that pushed Galileo to turn his telescope toward Jupiter's moons, that inspired Einstein to reimagine gravity as the curvature of space-time. In modern times, our relentless quest for understanding has led to technologies and discoveries that have reshaped civilization. The same principles that allowed us to study the distant galaxies also power GPS systems, medical imaging, and artificial intelligence. The search for extraterrestrial life has not only expanded our view of biology, but has also deepened our understanding of how life thrives in extreme conditions. Space exploration has fostered international collaboration as scientists from around the world work together to solve problems that are too vast for any one nation to tackle alone. Yet curiosity is not without its risks. Scientific progress often raises ethical dilemmas. How far should we go in modifying nature? Should we pursue artificial intelligence without fully understanding its consequences? Is it ethical to terraform other planets if it means altering a potentially pristine ecosystem? The history of exploration on Earth has shown that curiosity, when unchecked, can lead to exploitation. The same must not happen with our cosmic journey. As we expand our reach into space, we must do so with responsibility, ensuring that progress does not come at the cost of wisdom. The balance between knowledge and mystery. One of the greatest lessons of cosmic exploration is that knowledge and mystery are not opposing forces. They are two sides of the same coin. Every time we answer a question, new ones emerge. The discovery of dark matter and dark energy, for example, has not simplified our view of the universe. It has made it even stranger, revealing that we understand less about reality than we once thought. The paradoxes of quantum mechanics and general relativity show that our current models, while useful, are incomplete, and the sheer vastness of the universe suggests that even if we could explore for billions of years, there would always be more to discover. This realization forces us to embrace a kind of intellectual humility. Science is not about claiming absolute truths, but about refining our understanding. accepting that each generation's discoveries will be built upon and at times overturned by those that follow. It is a humbling thought that, just as we now view ancient cosmologies as primitive, future civilizations may one day look at our current theories as stepping stones toward an even deeper understanding. Yet, this is not a reason for despair, it is a reason for wonder. The fact that the universe is filled with mysteries means that there will always be more to explore, more to learn, more reasons to keep looking up at the night sky. It means that humanity will never truly reach the end of its journey, because the road itself is infinite. Lessons humanity can learn from cosmic exploration. Perhaps the most profound lesson that space teaches us is perspective. The famous pale blue dot photograph, taken by the Voyager 1 spacecraft, captures Earth as a tiny speck suspended in a sunbeam, a single pixel in the vast darkness of space. This image is more than just a picture. It is a reminder of our fragility and our unity. From space, the borders that divide nations disappear, political conflicts become trivial, and all of human history is condensed into a fraction of the cosmic timeline. It forces us to see that we are not separate from one another. We are part of the same journey, the same struggle, the same fragile world floating in an endless sea. This perspective can inspire a shift in how we approach global challenges. If we can work together to send rovers to Mars, land probes on comets, and build space telescopes that peer billions of years into the past, then surely we can work together to solve the problems that plague our planet: climate change, poverty, disease, and war. Space exploration teaches us that no problem is insurmountable when we apply the full force of human ingenuity and cooperation. Another lesson is patience. Scientific discovery is not instantaneous. It is the result of decades, sometimes centuries, of effort. The search for exoplanets capable of supporting life is still in its infancy, yet already thousands have been discovered. The study of dark matter may take generations before we find a definitive answer. The idea of interstellar travel may seem impossible today, but so did the moon landing just a century ago. If history has taught us anything, it is that the impossible only remains impossible until it is done. Finally, cosmic exploration teaches us about hope. The universe is vast and cold, but it is also full of possibilities. The discovery of extremophile organisms that thrive in conditions once thought inhospitable suggests that life could exist in places we never imagined. The realization that we are made of star stuff, that every atom in our bodies was forged in the heart of dying stars, connects us to the cosmos in a way that is both poetic and scientific. It means that we are not apart from the universe, we are a product of it, a way for the universe to know itself. Conclusion. In the end, the greatest lesson we can take from exploring the unknown is that the journey itself is what matters. Whether we find the ultimate answers or not, the pursuit of knowledge shapes us, refines us, and elevates us beyond mere survival. The universe is vast, and we are small, yet our capacity to question, to dream, and to wonder makes us significant. The unknown is not something to be feared, it is something to be embraced, for within it lies the endless potential of discovery. As we look ahead to the future, let us carry forward the lessons of cosmic exploration. Let us remain curious, let us remain humble, and let us continue to seek, not because we expect to find an end, but because the act of seeking itself is the greatest adventure of all. Whether the universe is infinite or has an edge, whether we ever find alien life or not, one truth remains constant. As long as we keep looking to the stars, we will never stop moving forward. The question of whether the universe has an edge, whether it is finite or infinite, and whether we will ever fully understand its fundamental nature remains one of the greatest mysteries of science. But should we even want a final, definitive answer? Is it better for the mystery to remain open-ended, driving us to continue exploring, questioning, and expanding our understanding of existence? Or should we seek closure, a single unifying theory that brings all cosmic questions to a definitive end? Throughout history, every scientific discovery has led not to finality, but to deeper layers of mystery, suggesting that the true nature of the universe may forever be beyond our grasp. And perhaps, in the grand scheme of things, that is exactly how it should be. The value of leaving questions unanswered. Some of the greatest scientific revolutions have come from asking the right questions, not necessarily from finding the answers. When Newton formulated the laws of motion and gravity, he revolutionized our understanding of how objects move, yet he had no explanation for why gravity existed. That question remained unanswered for centuries, until Einstein's theory of general relativity provided a new perspective, redefining gravity not as a force, but as the curvature of space-time. Even Einstein, however, left questions unanswered. His equations suggested the possibility of black holes, singularities where space and time break down, but he doubted their physical existence. It was only later, through observation and new mathematical approaches, that black holes were confirmed as real cosmic phenomena. This pattern repeats throughout history. The discovery of quantum mechanics in the early 20th century shattered the certainty of classical physics, revealing a world of probability, superposition, and entanglement. While quantum mechanics has given rise to technological advancements such as semiconductors and quantum computing, it has also introduced profound mysteries. Why does observation affect reality? Is there a deeper order beneath quantum randomness? Does reality exist independently of measurement? These questions remain unresolved, yet they continue to fuel new research, leading to even greater breakthroughs. If we were to find a final answer to the universe, a single theory could explain everything. If we could definitively map the structure of space-time, if we could determine whether the universe is infinite or has an edge, would that truly be the end of inquiry? Or would it simply lead to new questions that we haven't yet imagined? The pursuit of knowledge thrives on uncertainty, and it is this uncertainty that keeps science alive. If the universe is infinite, then so too is the possibility of discovery. Summary of the biggest takeaways. Throughout our journey into the mysteries of the universe, several key themes have emerged. The universe is stranger than we ever imagined. Every new discovery challenges our assumptions. Dark matter and dark energy suggest that the majority of the universe is made of something we cannot directly observe. The idea of a multiverse suggests that our universe may be one of many, with different laws of physics governing each. The possibility that space-time is emergent rather than fundamental reshapes our understanding of what reality truly is. Whether the universe is infinite or finite, whether it has an edge or loops back onto itself, one thing is certain: it is far more complex than we ever expected. Curiosity is the driving force of progress. Science has never been about having all the answers. It has always been about asking better questions. The most significant advancements in physics, astronomy, and cosmology have come from challenging existing models, testing new ideas, and refining our understanding based on observation. The fact that we do not yet know everything is not a failure. It is the very reason why we continue to explore. The universe challenges our perception of reality. The study of space forces us to confront questions that go beyond science and into philosophy. If time is not fundamental, what does that mean for our experience of past, present, and future? If parallel universes exist, what does that mean for our understanding of identity and choice? If the universe is a holographic projection, what does that mean for the nature of consciousness? These are questions that blur the lines between physics, metaphysics, and existential thought. The more we discover, the more there is to discover. The cosmic microwave background gave us a glimpse into the early universe, but it also revealed anomalies we do not yet understand. The detection of exoplanets has expanded our knowledge of planetary systems, but it has also raised new questions about habitability and the likelihood of life elsewhere. Gravitational wave astronomy has opened a new way to observe the universe, yet it is only the beginning of an entirely new field of exploration. Every discovery expands our horizons rather than narrowing them. We are part of something vast, yet meaningful. Whether the universe is infinite or not, whether we are alone or one of many intelligent species, the simple fact that we can contemplate these questions is extraordinary. We are made of the same elements as the stars, and our existence is intertwined with the evolution of the cosmos itself. If the universe is a vast and complex puzzle, then we are both the product of that puzzle and the ones trying to solve it. Final thoughts on the infinite possibilities of space. Should the mystery remain open-ended? In a way, it already is. Every time we think we are close to understanding the true nature of reality, the universe reminds us that we have only begun to scratch the surface. And that is not a limitation, it is an invitation. The infinite possibilities of space reflect the infinite potential of human imagination. Our search for knowledge is not just about answering scientific questions. It is about expanding our consciousness, challenging our perspectives, and embracing the wonder of existence. Perhaps the greatest lesson of all is that the journey itself, the act of seeking, of wondering, of daring to ask, "What if?" is more important than any single answer we may find. The universe may have an edge, or it may stretch infinitely beyond our grasp. We may one day discover definitive proof of a multiverse, or we may find that our reality is far more unique than we ever imagined. We may uncover the nature of dark matter and dark energy, or we may discover that they are merely shadows of something even more profound. But regardless of what we learn, the most important truth remains. As long as we continue to ask, to explore, and to dream, the mystery of the universe will always be alive. And that, perhaps, is the most beautiful conclusion of all. Not an end, but an endless horizon, waiting to be explored.